Hello, and welcome to Physics for Play. In today's episode, we're going to show you how to read off various properties from a wave function, things like the wavelength, the wave speed, the period, and we'll be doing that by going through a problem in Bikifi and Barrett's electromagnetic vibrations, waves, and radiation. Let's get started. So we are going to do problem 2.1 in Bikifi and Barrett. And you can see here that the problem states that we have 2 points on a string that are observed to be traveling as a wave passes them. So we're looking at 2 individual points on a string. The points are located at x equals 0 and x equals 1 meter. The transverse motions of the 2 points are found to be as follows. So you've got point 1 has an amplitude of 0.2 times sine pi t, or sine 3 pi t, excuse me. And the second point, y2, has an amplitude of 0.2 times the sine of 3 pi t, but this time shifted in phase by pi over 8. We are to find the frequency, the wavelength, the wave speed, the direction of travel for the wave, and then Part E wants us to look at a wave pulse of a triangular shape and draw a graph of it and its velocity. So let's go ahead and get started. We want to find first the wave frequency, which we should be able to tell here just by looking at this 3 pi t in the sine function. So the frequency can be read directly off the transverse motion equations because we know that if you have looked at any of the wave on a string equations before, you know that the argument of the sine function is equal to the sine of 2 pi times the frequency times time. Therefore, we can find the frequency simply by solving this equation for the frequency. So 2 pi ft has to equal the argument of our sine function, which is 3 pi t. This is easy enough algebra to do, but just to show you how to do it in Mathematica, we'll use the solve function to come up with an answer that's a solution for f, and we can see the frequency is just 1.5. You just get that by dividing 3 pi t divided by 2 pi t to move that over to the other side. You get 1.5 as a remainder. Next, we will want to find the wavelength, and to do that, we're going to be looking at the phase separation between these 2 waves. So these 2 waves are out of phase. That's going to happen since they're not at the same point, and they're going to be out of phase by a certain amount depending on the wavelength. Now this part gets very tricky because we have a sine function and sine functions are periodic. So we've got to take that into account. Also, the wave could be traveling in the positive or the negative direction, and we've got to take that into account as well. So the 2 points are separated by 1 meter. If the wave is traveling in the negative x direction, then the point at x equals 1 is going to be behind in phase. Because the wave is traveling to the left, the point to the right is going to be behind in phase. And it's going to be behind by an amount pi over 8, but that's not going to be the only answer. Just because I have a pi over 8 here doesn't mean that's the phase difference, because the sine wave is periodic, it could be off by that plus any multiple of 2 pi. Since it's periodic, the wave is going to repeat every 2 pi in period, or every 2 pi in phase. So we need to account for that here. So we're just going to tack on it plus 2 pi n. Here, the n is an integer, and again, it arises because the wave is periodic. So we have multiple wavelengths that will work as a solution. We can find what those values are, just like we did with the frequency. We're going to find we're going to use the solve function. All I'm going to do here is I am going to say that we know that 2 pi is 1 wavelength. So I am just going to use my ratios here to say that my difference in phase, I have to have a difference of 1 complete cycle. So 1 complete cycle is a full wavelength. Similarly, in phase, that would be 2 pi, and I've got to have that off by this amount. So we're going to solve this equation for the wavelength in meters. When you do that, you will see, actually I already evaluated it here. You will see we get a wavelength that is given by 16 divided by 1 plus 16n, and the results will be in meters here. So let's actually show that that's really what's going on here. So I'm going to do that by creating 2 points, y1 and y2 of t, which are just going to be given by let's keep that open, which are just given by the functions defined in the problem. So 0.2 sine 3 pi t, 0.2 sine 3 pi t plus pi over 8. And I've taken the liberty of typing this out, but all I am going to do is I'm going to create a wave function. So here it's 0.2 is the amplitude, sine 2 pi x over lambda plus frequency times time. I will plug in the values that we found here. So lambda is 16 plus 1 over 16n, lambda is 16 plus 1 over 16n. The frequency we found was 1.5. So the frequency here is going to be 1.5. We're going to plot this wave from -1 to 2 with a plot range of -0.3 to 0.3. So we cover that 0.2 amplitude. I'll put it in a frame just to make it look nice. And I'm also going to put 2 disks in here, one at x equals 0, which will be moving with the function y, 1 of t, and one at x equals 1, which will be moving with a function y2 of t. And the reason we'll do this is to show that for various n, we'll wrap this in a manipulate so that we can see this for various n. We'll show that that lines up for all time as the wave passes. You can see the wave is passing to the negative x direction. I can see that if I up the mode number. And you can see my points at x equals 0 and x equal 1 just match up with that wave very nicely, and it will do that for any of the n's that show up in the wavelength. So I can increase my n, and you can see those 2 points just map out correctly the shape of the wave. And the only way that this would work is if the wavelength and the frequency that I had were correct. Now, this is a nice time to point out that this is why using something like a Mathematica or some sort of tool where you can do your computations and animations is really useful. Because without this, if I'm just doing this problem on pen and paper, I am never going to see this. It's going to be really hard to verify that I've got the right solution. But here you can just animate it and show that you've got the right answer. So highly recommend solving your problems like this using computation, using computer tools, so that you can actually see what's going on. But let me get off my soapbox for a second, because that is not the only solution for this wavelength. Because right now you can see that the wave is traveling in the negative x direction. I could also have the wave traveling in the positive x direction. So we're going to look at that case now. If the wave is traveling in the positive x direction, then the point at x equals 1 is going to be ahead in phase by an amount pi over x plus 2 pi n. Or equivalently, it'll be behind in phase by an amount 15 pi over 8 plus 2 pi n, because it's, again, the wave is traveling in the opposite direction now. So I can think of this point being ahead or behind in phase, but I've got to shift it by 2 pi if I'm gonna do that. So we can see that here. Here n is an integer. again, the 2 pi arises, the 2 pi n arises because we can have, because the wave is periodic. So all I'm going to do is plug in 15 pi over 8 plus 2 pi n is equivalent to 2 pi in phase, which is equivalent to 1 cycle, which is equivalent to the wavelength lambda. So I can set up this ratio and solve for the wavelength. You can see this time we get a slightly different wavelength. We've got, here we had 16 plus 1 over 16n before. Now it's 16 plus 1, 16 over 15 plus 16n if the wave is traveling in the positive x direction. Again, we can write this out. All I have to do is change the wavelength equation that I had before, put a minus sign in front of the x over lambda so that the wave is traveling in the opposite direction. It's the same code that I used to make this plot, except now when I make this plot of the wave traveling, it'll be in the positive x direction. So let me run that. And this should go ahead and move in the positive x direction. Again, my wavelength is going to be a little bit different because it's out of phase a certain amount, because whether you're at position x equals 0 or x equals 1, how much you're out of phase depends on which way the wave is traveling. So that's going to mess with your wavelengths a little bit. And you can see that they match up here if the wave is moving in the positive direction. Alrighty. So we've done, we've shown 2 different ways to compute the wavelengths, and we've shown that for each way we've got multiple wavelengths because it's periodic. So if we look back at our original question, with what speed does the wave travel? It's a little bit of a trick question because there's multiple speeds that work, and there's multiple wavelengths that work. And to get the wave speed, we can just use our wave speed as wavelength times frequency. But because we found multiple wavelengths will work and speed is dependent on the wavelength, then we're going to have multiple speeds that will work as well. So we've got 2 different solutions that we came up with. We came up with a solution for when the wave was moving in the negative direction. We came up with a solution for when the wave is moving in the positive direction. So I've got to come up with 2 different answers for the wave speeds, which I will get by just replacing the wavelength with the positive solution or the negative solution. And I'll also replace the solution for the frequency in here, which is easy enough to do. I'll just put that in. And so your wave speeds given for the positive direction will be 24 over 15 plus 16n. And in the negative direction, it'll be 24 over 1 plus 16n. And these will be in meters per second, given the units in the problem. What are the directions? What was the direction of travel? Doing part D. Which way is the wave traveling? Show how you reach this conclusion. Well, we've already kind of done that. We've shown that it really depends on what wavelength you get, but the direction of travel, the wave can be moving in either direction. But you get different solutions depending on which direction you assume it's going in. Lastly, we've got this part E. We've got a symmetric triangular pulse of maximum height 0.4 with a total length 0.1, or total length of 1 meter, moving to the right with a pulse that's entirely located between x equals 1 and x equals 0 at time t equals 0. So here it wants us to draw a graph of the transverse velocity versus time at x equals x2 equals 1 meter. So we're going to look at what the point on the string located at 1 meter is going to be doing. And we're going to assume this pulse as the speed that we calculated in part C. Again, a little bit of a trick question because there are multiple wave speeds that would have worked for that. So we'll do this problem in a few parts. I am going to assume that n is 0 and that we're moving in the positive x direction. Therefore, the wave speed, as we computed before, here I'm plugging in n equals 0, moving in the positive direction. replacing wave speed, which is equal to the wavelength times the frequency, by the solutions we found for the wavelength and the frequency here. So we do that, we get a wave speed of 1.6. We're going to define the triangular wave shape for the pulse using a piecewise function. So we're going to define that as triangular pulse wave function as a function of x. It's a piecewise function, so it's going to be connected by different pieces. So outside the wave pulse, it's going to be 0, and that'll be for x less than 0, which is ahead of before the wave pulse, and it'll also be 0 for x greater than or equal to. Actually, this should be 1, not 0. For anything greater than 1, it'll be 0. Anything greater than 1 or less than 0, we have no wave pulse. But if x is less than 0.5 or between 0.5 and 1, then I've got just two different straight line shapes, and we'll show that this actually looks like a triangular wave pulse because I will animate a plot of that wave here. So just to show you that this actually works, you can see an animation of it here. Just a triangular wave pulse moving to the right. And here we can tell it is moving with a speed v because I've put a phase shift that is equal to vt moving in the positive x direction. Okay, so we've got the shape of our wave. We've got our wave function. The last thing I want to do, or the next thing I want to do, is compute the transverse velocity of that wave by taking the time derivative. Again, I want to plot that transverse velocity. I want to make a graph of it for the wave at 0 and 1, for the wave as it passes by the point x equals 1 meter. So I'm just going to take the partial derivative with respect to time of that function, and I'm going to replace x with x equals 1. I do that, and you see I get a piecewise function back. And to make a plot of that graph, we'll just plug this piecewise function into our plot, and we'll see what that looks like. So you can see, and it might actually help if I show what the animation looks like. So I am looking at what this point on the string, point 1, is doing at any given time. And when I start the wave, so right now it's at 0, but then that point starts increasing, it goes up, and then it starts going back down. So if we look at our plot, you can see before the wave gets there, the point on the string at x equals 1 meter is not moving at all. It has 0 transverse velocity. Then when the triangular wave pulse gets there, all of a sudden it jumps up, it has a positive velocity here. And you can see, if I look over here, we can actually see what that velocity is. It's got a value of 1.28. Then once it gets past the peak, the point starts coming back down, has a constant negative velocity. Again, that's just due to the triangular shape of the wave. And then when the wave pulse passes, it has a velocity of x equals 0. Now, we can make that a little bit easier to see by plotting our wave pulse with a graphic that actually highlights what that point on the string is doing. So you can see, let me pause that here. We're going to be watching that green point, and you'll see exactly what happens here. So the green point has 0 velocity before the wave pulse gets there. And you can see it has 0 velocity before the wave pulse gets there. Then when the wave pulse does get there, it goes up with a constant velocity. So it's going up with a constant velocity here. Then you see it jumps down, goes to a constant negative velocity. Constant negative velocity, it goes down. See that again, constant negative velocity going down. Then once the wave pulse is passed, the green point doesn't move, it has no more velocity. 0 velocity, positive to negative to 0 velocity, just like we see in our graph. 0 velocity, positive constant velocity, negative constant velocity to 0 velocity. Again, let me jump on my soapbox for just a second. Without without a tool like this, you would not be able to really visualize this. You could figure it out by thinking about it, but it's so much more powerful to actually see the animations, to do the simulation of what's really going on. So this video is a little long, so we're going to stop here. Please like the video if you liked it, and if you'd like to see more of these, please click subscribe.